Welcome, dear listener, to this quiet corner of the cosmos, a place where the soft hum of the universe surrounds you and the gentle light of distant stars finds its way to you through the careful eye of the James Webb Space Telescope. Tonight, we invite you to let the grandeur of deep space carry you toward rest, as we journey through 110 carefully gathered facts about one of humanity's most remarkable scientific instruments and the breathtaking discoveries it has gifted us. Allow the enormity of these ancient galaxies, the slow dance of forming stars, and the deep silence between worlds to ease the tension from your body and quiet the thoughts of your day. There is nothing you need to do, nowhere you need to be. Only here, drifting softly through the universe, one gentle breath at a time. The James Webb Space Telescope, often referred to simply as JWST, represents the culmination of more than 2 decades of collaborative planning, engineering, and aspiration that began in the late 1990s. The idea for a successor to the Hubble Space Telescope was first formally discussed at a Space Telescope Science Institute workshop in 1989, where astronomers began imagining an observatory powerful enough to peer into the earliest moments of the universe. Over the following years, hundreds of scientists, engineers, and visionaries from NASA, the European Space Agency, and the Canadian Space Agency quietly shaped this dream into a concrete plan. The telescope's name honors James E. Webb, NASA's administrator from 1961 to 1968, who guided the agency through the formative years of the Apollo program with patience and steady purpose. At the heart of the James Webb Space Telescope lies its primary mirror, a stunning hexagonal mosaic composed of 18 individual segments, each carefully coated in a microscopically thin layer of gold. The entire mirror, when assembled, spans approximately 6.5 meters in diameter, more than twice the diameter of the Hubble Space Telescope's primary mirror, giving JWST a light-collecting area of roughly 25 square meters. Each of the 18 beryllium segments was polished to extraordinary precision, with surface irregularities no greater than a few tens of nanometers, a smoothness so fine it is difficult to comprehend without careful reflection. The gold coating was chosen specifically for its exceptional ability to reflect infrared light, the very wavelengths that carry information from the universe's earliest and most distant objects. The 18 mirror segments of the James Webb Space Telescope are crafted from beryllium, a lightweight silvery metal chosen for its remarkable behavior in the extreme cold of deep space. Beryllium is exceptionally stiff for its weight, meaning the mirror segments retain their precise parabolic shape even as temperatures drop to approximately negative 233 degrees Celsius during telescope operation. This thermal stability was essential, because any slight warping of the mirror surface would scatter infrared light and introduce distortions that would compromise the telescope's ability to form sharp, accurate images. Each beryllium blank was carefully machined, ground, and polished over many months before receiving its reflective gold coating, representing some of the most exacting optical craftsmanship ever attempted. One of the most visually distinctive features of the James Webb Space Telescope is its enormous 5-layer sunshield, a structure roughly the size of a tennis court when fully deployed, measuring approximately 21 by 14 meters. Each of the 5 layers is made from a material called Captain, coated on one side with aluminum and on the sunward side with silicon, allowing the shield to reflect and radiate away the intense heat of the sun with exceptional efficiency. The layers are carefully spaced apart so that heat from each warmer layer can radiate away into space before reaching the next, creating a cascading cooling effect that drops the temperature from roughly 85 degrees Celsius on the sun-facing side to approximately negative 233 degrees Celsius on the telescope side. This delicate, kite-shaped parasol makes the telescope's infrared observations possible by keeping its mirrors and instruments in a state of profound, sustained cold. Unlike the Hubble Space Telescope, which observed primarily in visible and ultraviolet light, the James Webb Space Telescope is designed to see the universe almost exclusively in infrared wavelengths, spanning from 0.6 to 28 micrometers across its suite of instruments. Infrared light is invisible to the human eye but carries an enormous wealth of information about cool objects, distant galaxies whose light has been stretched by the expansion of the universe, and objects hidden behind clouds of dust that would block visible light entirely. By detecting infrared radiation, JWST can look through the dusty cocoons surrounding newly forming stars, observe the atmospheric compositions of planets in other solar systems, and capture light from galaxies so distant that it left them when the universe was less than 1 billion years old. The telescope's entire design, from the temperature of its mirrors to the architecture of its sunshield, is optimized around this singular, profound capability. The James Webb Space Telescope orbits not around the Earth itself, but around a gravitational equilibrium point in space known as the Second Sun-Earth Lagrange Point, or L2, located approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this specific location, the gravitational pull of the Sun and Earth, combined with the centrifugal effect of the telescope's orbit, keeps JWST in a stable position that allows it to face away from both the Sun and Earth simultaneously. This configuration is ideal for the telescope's operations because it keeps the bright heat sources of the Sun, Earth, and Moon all on the same side, behind the sunshield, leaving the cold, dark universe spread out before the telescope's golden mirror. The journey to L2 took approximately 29 days after launch, and the telescope now traces a gentle halo orbit around this quiet gravitational harbor. Nestled behind the golden primary mirror of the James Webb Space Telescope are 4 principal scientific instruments, each designed to capture different aspects of infrared light and serve distinct observational purposes. The near-infrared camera, known as NIRCam, is the telescope's primary imaging instrument, capturing wide-field images of galaxies, star clusters, and other astronomical objects in near-infrared wavelengths. The Near-Infrared Spectrograph, or NIR-SPEC, can simultaneously observe the spectra of up to 100 objects at once, measuring the precise chemical fingerprints embedded in their light. The mid-infrared instrument, called MIRI, observes at longer infrared wavelengths and is the only instrument that requires active cooling by a specialized cryocolor to reach its operational temperature of approximately negative 266 degrees Celsius, just a few degrees above absolute zero. Completing the suite of instruments aboard the James Webb Space Telescope is the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, a dual-purpose instrument contributed by the Canadian Space Agency that plays a quietly essential role in the telescope's operations. The Fine Guidance Sensor portion uses bright stars as reference points to maintain the telescope's pointing stability with extraordinary accuracy, keeping the mirror aimed at its target with a precision equivalent to holding a laser beam steady on a dime from several kilometers away. The nearest portion provides additional spectroscopic capabilities, particularly useful for studying the atmospheres of exoplanets as they pass in front of their host stars, a technique known as transmission spectroscopy. Together, these instruments give JWST a remarkable range of observational modes, allowing it to pursue questions from the formation of the first stars to the chemistry of worlds beyond our own solar system. Because the James Webb Space Telescope is far too large to fit inside any existing rocket fairing in its operational configuration, engineers designed it to fold upon itself in a carefully choreographed origami arrangement, then slowly unfold over the first 2 weeks after launch in what NASA described as one of the most complex deployment sequences ever attempted in space. The primary mirror's 18 segments were folded inward like the petals of a flower closing for the night, while the sunshield was carefully packed into a compact stack and the secondary mirror was folded flat against the telescope's body. After launch on December 25, 2021, the telescope gradually unfolded over 29 sequential deployment steps, each one critical to the mission's success, with the sunshield alone requiring a carefully choreographed sequence of more than 140 individual mechanisms. All 29 major deployment steps were completed successfully by January 8, 2022, representing a profound milestone in space engineering. The James Webb Space Telescope began its journey into the cosmos aboard an Ariane 5 rocket, launching from the Guiana Space Center in Kourou, French Guiana, on the morning of December 25, 2021, a date that carried a quiet poetic resonance as a gift to the world of science. The Ariane 5 was selected for its proven reliability and its ability to deliver the telescope to its precise trajectory with exceptional accuracy, and it performed so well that the launch used less fuel than planned, an outcome that significantly extended JWST's expected operational lifetime well beyond the original 10-year design goal. The launch placed JWST on a trajectory toward L2 with a velocity so precise that only 3 small mid-course correction burns were needed to refine the path, far fewer than the maximum of 5 that had been planned for in contingency. Within minutes of separating from the rocket, the telescope began deploying its solar panels and communicating with ground stations, signaling the beginning of its long-anticipated journey. On July 12, 2022, the James Webb Space Telescope released its first package of full-color scientific images to the world, and among them was a deep-field image of a galaxy cluster known as SMACS 0723 that immediately captured the quiet wonder of astronomers and the general public alike. The image revealed thousands of galaxies, some appearing as crisp spirals and glowing ellipses, others stretched and distorted into luminous arcs by the gravitational lensing effect of the foreground cluster, all contained within a patch of sky roughly the size of a grain of sand held at arm's length. Some of the tiny, reddened smudges visible in the image represent galaxies whose light has been traveling toward us for more than 13 billion years, carrying the story of the universe's earliest chapters. The image was released at a White House briefing, underscoring the profound sense of collective human achievement that it represented. Among the first images released by the James Webb Space Telescope was a breathtaking mosaic of Stephan's Quintet, a compact group of 5 galaxies located approximately 290 million light-years away in the constellation Pegasus, 3 of which are engaged in a slow, graceful gravitational dance that will ultimately lead to their merger. The JWST image captured this quintet in extraordinary detail, revealing streams of gas and dust stretched between the galaxies like the delicate filaments of a cosmic web, glowing in hues of gold, amber, and deep rose. A massive shockwave, created where one of the galaxies is plunging into the group at tremendous speed, was seen as a broad arc of heated gas spanning hundreds of thousands of light-years. The image's sheer scale, composed of roughly 1,000 separate image files containing approximately 150 million pixels, made it the largest image JWST had released at that time. The Southern Ring Nebula, a planetary nebula located approximately 2,000 light-years from Earth, was among the first objects captured in detail by the James Webb Space Telescope, and the images revealed unexpected complexity within its layered shells of gas and dust. In near-infrared light, the nebula appeared as a series of concentric rings of glowing material illuminated by two stars at its center, while the mid-infrared images from MIRI revealed one of those central stars to be surrounded by a dusty disk, a detail that had not been apparent in previous observations. The cool outer star at the center was shown to have been shedding material into space over many thousands of years, sculpting the intricate layered structure of the nebula into its current form. The images illustrated how JWST's ability to observe at multiple infrared wavelengths simultaneously could reveal layers of astrophysical detail that had previously required many separate observations with different instruments. Perhaps the most visually striking of the early JWST release images was the so-called cosmic cliffs, a portion of the Carina Nebula located approximately 7,600 light-years from Earth, where towering pillars of gas and dust rise like ancient coastal bluffs against a blazing background of ionized gas. In previous Hubble images, these same pillars had appeared grand and ancient. In the JWST image, they were revealed to be alive with activity, peppered with dozens of young stars in the process of forming, their jets and outflows carving subtle cavities into the surrounding gas. The image was rendered in false color to represent different infrared wavelengths, with warm oranges and yellows depicting the densest regions of dust-laden gas and cool blues indicating hotter, more diffused material. The sheer number of previously hidden young stars revealed in the image underscored JWST's unique ability to peer through the dusty curtains that hide the earliest stages of stellar birth. Alongside its first release images, the James Webb Space Telescope also unveiled what was at the time the most detailed infrared spectrum ever obtained of a planet outside our solar system, the spectrum of WSP 96b. A giant gas planet orbiting a Sun-like star approximately 1,150 light-years from Earth. The spectrum, which breaks starlight into its constituent wavelengths much like a prism separates white light into a rainbow, revealed the unmistakable signatures of water vapor in the planet's atmosphere, along with hints of haze and clouds at high altitudes. What made this observation particularly remarkable was not merely the detection of water, which had been found in WSP 96b's atmosphere before, but the level of detail in the spectral data, which showed the precise shapes of water absorption features with a clarity that previous instruments could not achieve. This early demonstration established JWST as a transformative tool for the emerging field of exoplanet atmospheric science. Before any scientific observations could be made, the James Webb Space Telescope underwent a patient and methodical process of mirror alignment over several months following its launch, during which the 18 individual mirror segments were carefully adjusted until they acted as a single unified optical surface. The process began in early February 2022 when the telescope first captured images of a single bright star scattered into 18 separate points of light, one for each misaligned segment, and culminated in late March when all 18 reflections merged into one sharp, precise image. Each mirror segment could be adjusted in 7 different ways using tiny actuators, with the finest adjustments measured in nanometers, a precision equivalent to the width of a few atoms. The engineers and scientists guiding this process worked with extraordinary care and patience, knowing that any error could compromise the telescope's long-term performance. Following its launch and the completion of mirror deployment and cooling, the James Webb Space Telescope entered a commissioning period lasting approximately 6 months, during which every instrument and system was carefully tested, calibrated, and validated against the extraordinary precision the mission required. During this period, scientists and engineers ran a comprehensive suite of tests including optical alignment verification, detector characterization, filter calibration, and end-to-end observing mode testing, producing a detailed portrait of the telescope's capabilities and any quirks that observers would need to account for. Some early results during commissioning, including images of star-forming regions and spectra of distant galaxies, were so crisp and detailed that they immediately surpassed the expectations of the mission team. The commissioning phase concluded in late June 2022, and the telescope formally began its science operations with a performance that exceeded the engineering requirements set more than 2 decades earlier. From the very earliest stages of its operation, the James Webb Space Telescope consistently demonstrated performance that exceeded the specifications set during its design phase, bringing both relief and quiet delight to the large community of scientists who had devoted portions of their careers to the mission. The telescope's mirror alignment achieved a wavefront error, a measure of how far the mirror surface deviates from its ideal shape, of approximately 57 nanometers root mean square, comfortably better than the 150 nanometer requirement. The sensitivity of its instruments likewise surpassed predictions, meaning that JWST could reach the faintest, most distant objects in less observing time than originally planned, effectively multiplying the scientific output the mission could achieve in its lifetime. These early indicators suggested that the James Webb Space Telescope would fulfill its promise as a generational instrument, one whose discoveries would unfold gradually over decades of careful, patient observation. The James Webb Space Telescope must hold its gaze upon a single target with extraordinary steadiness throughout an observation, maintaining a pointing precision of approximately 1.4 milliarcseconds, a unit of angular measure so tiny that it corresponds to holding a laser pointer steady on a dime from a distance of roughly 2 kilometers. This stability is achieved through a combination of reaction wheels, spinning gyroscopes that can adjust the telescope's orientation by varying their speed, and the fine guidance sensor, which continuously monitors bright guide stars and makes tiny corrections to keep the telescope precisely aimed. During observations of particularly faint objects, any drift in pointing would smear the telescope's images and degrade the quality of its spectra, so this steadiness is essential to the science. The remarkable pointing stability was maintained throughout the commissioning period and into science operations, contributing directly to the sharpness and precision of JWST's earliest images. As the James Webb Space Telescope journeyed toward its home at the L2 point following launch, it underwent a gradual and carefully managed cooling process that brought its mirrors and instruments down from the warmth of Earth's environment to the frigid temperatures required for infrared observation. The passive cooling of the telescope, relying on the sunshield to block heat from the Sun, Earth, and Moon, brought most of the telescope's structure down to approximately -233 degrees Celsius over the weeks following deployment. The MIRI instrument, which observes at the longest infrared wavelengths and requires the coldest operating temperature of all the instruments, was additionally cooled by a closed-cycle helium cryocolor that brought it down to approximately -266 degrees Celsius, just about 7 degrees above absolute zero. This slow, quiet descent into deep cold was a prerequisite for the telescope's ability to observe the faint infrared glow of the universe's most distant and ancient objects. When the James Webb Space Telescope observes distant galaxies, it is not merely looking across space but traveling backward through time, because the light it receives from remote objects has been journeying through the expanding universe for billions of years before arriving at the telescope's golden mirror. The most distant galaxies JWST can observe emitted their light when the universe was only a few 100 million years old, a period so early in cosmic history that it precedes the formation of most of the heavy elements, when the first stars were just igniting in the formless darkness. As light travels across such vast distances, the expansion of the universe stretches it to longer wavelengths through a process known as redshift, shifting visible light into the infrared range that JWST is designed to detect. This profound connection between distance, time, and wavelength means that JWST's ability to see in infrared light is precisely what allows it to look deepest into the universe's past. The James Webb Space Telescope provided compelling confirmation of the extreme distance of GNZ11, a galaxy that had been one of the most distant known objects when identified by the Hubble Space Telescope, but whose distance had rested on relatively uncertain photometric measurements rather than definitive spectroscopic evidence. JWST's NIR-SPEC instrument captured a spectrum of GNZ11 that clearly showed the galaxy's emission lines redshifted to a factor of approximately Z equals 10.6, placing it at a distance corresponding to a time when the universe was only about 430 million years old. Beyond confirming the distance, the JWST spectrum revealed that GNZ11 contains an unusually dense and luminous core that may be powered by a rapidly accreting black hole, making it not just an ancient but an actively dynamic system. These findings added depth and nuance to our understanding of how the earliest massive galaxies and their central black holes grew so rapidly in the young universe. In 2024, the James Webb Space Telescope set a new record for the most distant spectroscopically confirmed galaxy ever observed, a system designated JADES GSZ14-0, whose light was found to have originated when the universe was only approximately 290 million years old, a mere 2% of its current age. Discovered as part of the JWST Advanced Deep Extragalactic Survey, known as JADES, this remarkable galaxy showed evidence of containing significantly more mass and having formed significantly more stars than theoretical models had predicted would be possible at such an early cosmic epoch. The detection of oxygen emission in the galaxy spectrum was particularly striking, because the presence of heavier elements like oxygen implies that at least one prior generation of stars had already been born, lived, and dispersed their material into the galaxy's gas by that point in time. This single observation challenged existing frameworks for understanding how quickly the earliest stars and galaxies could form and enrich their surroundings. One of the most striking and broadly discussed findings from the early JWST deep field observations was the discovery that luminous, well-structured galaxies appear to exist in much greater numbers at very high redshifts than standard cosmological models had predicted, suggesting that the universe formed large and organized structures more quickly than previously understood. Multiple independent teams of astronomers analyzing JWST deep field images identified candidate galaxies at redshifts of 10 and above, the epoch when the universe was less than 500 million years old, that appeared too bright and too massive to fit comfortably within existing theoretical frameworks. These observations generated a lively and productive scientific discussion about whether the standard cosmological model needed revision, or whether the candidate redshifts had been overestimated, or whether new physical processes such as unusually efficient star formation were operating in the early universe. Subsequent spectroscopic confirmation of some of these galaxies supported the view that early galaxy formation was indeed more vigorous and rapid than previously anticipated. Among the central scientific goals of the James Webb Space Telescope is understanding the epoch of reionization, a transformative period in the universe's history between approximately 400 million and 1 billion years after the Big Bang, when the first stars and galaxies gradually ionized the neutral hydrogen gas that had filled the cosmos since the era of recombination. During this epoch, the universe transitioned from an opaque fog of neutral gas to the transparent, star-filled cosmos we observe today, and JWST is uniquely positioned to study the galaxies that provided the ultraviolet radiation responsible for this transformation. Early JWST observations have identified candidate ionizing sources, compact, intensely star-forming galaxies that appear to have been significant contributors to reionization, helping to illuminate the physical processes that cleared the cosmic fog. Understanding the timing, sources, and progression of reionization is one of the fundamental chapters in the history of the universe, and JWST is providing the first truly detailed glimpses into this ancient transition. The James Webb Space Telescope frequently takes advantage of a phenomenon called gravitational lensing, the bending of light by massive objects such as galaxy clusters, which acts as a natural magnifying glass that amplifies the light of even more distant galaxies lying behind the cluster along the line of sight. In the famous deep field image of SMACS 0723, the foreground galaxy cluster bends and distorts the light of background galaxies, creating arc-shaped and sometimes ring-shaped images that can magnify the background's objects by factors of tens or even hundreds. This natural amplification allows JWST to observe galaxies that would otherwise be far too faint to detect, effectively extending the telescope's reach deeper into the early universe than would otherwise be possible. The combination of JWST's extraordinary sensitivity and the lensing magnification provided by massive foreground clusters has proven to be one of the most productive pairings in modern astronomical observation. The James Webb Space Telescope has enabled astronomers to study the shapes and internal structures of galaxies at high redshifts with a level of detail that was previously achievable only for relatively nearby galaxies, revealing that many early galaxies have surprising and diverse morphologies. Some distant galaxies observed by JWST appear as compact, dense spheroids quite unlike the graceful spiral or elliptical forms that dominate the local universe, suggesting that the processes shaping galaxy structure were quite different in the early cosmos. Others show elongated, irregular forms that may reflect the influence of frequent galaxy mergers and the chaotic environment of the young universe, where dark matter halos were rapidly accreting gas and colliding. A significant subset of early galaxies observed by JWST appear as smooth, disk-like structures, a form once thought to require more time to develop than the early universe had available, prompting a productive reassessment of galaxy formation theories. Observations from the James Webb Space Telescope have allowed scientists to measure the rate at which stars were forming in distant galaxies with unprecedented precision, revealing that some early systems were forming stars at rates that vastly exceeded those seen in comparable galaxies in the modern universe. By analyzing specific emission lines in the spectra of these galaxies, particularly lines produced by hydrogen and oxygen gas that has been heated by intense ultraviolet radiation from young, massive stars, astronomers can estimate how rapidly new stellar material is being assembled within a given galaxy. Some of the high redshift galaxies identified by JWST appear to have been forming stars at rates of tens or even hundreds of solar masses per year, extraordinary productivity in systems that had existed for less than 1 billion years. These measurements provide direct evidence for the vigorous and rapid buildup of stellar mass in the early universe that theoretical models have long predicted but that observations had previously struggled to confirm. The James Webb Space Telescope has uncovered evidence for massive black holes existing at extremely early cosmic times, challenging existing models of how quickly these extraordinary objects could have assembled their enormous masses. Observations of several high redshift galaxies have revealed spectral signatures consistent with the presence of actively accreting supermassive black holes, known as active galactic nuclei, at redshifts where the universe was only a few 100 million years old. The existence of such massive black holes so early in cosmic history has long been a theoretical puzzle, because standard black hole growth models require significant time to build up mass through accretion. JWST's spectroscopic capabilities have allowed astronomers to identify and characterize these early black holes with far greater confidence than was previously possible, setting the stage for a deeper theoretical understanding of the earliest cosmic engines. The JWST Advanced Deep Extragalactic Survey, known as JADES, represents one of the deepest and most comprehensive programs of galaxy observation that the James Webb Space Telescope has conducted, devoting hundreds of hours of observing time to a pair of carefully selected fields that include the region covered by the Hubble Space Telescope's iconic ultra-deep field. The JADES program combines deep imaging from NIRCam with extensive spectroscopic follow-up from NIRSpec, allowing researchers to not only detect thousands of faint, distant galaxies but also to measure the redshifts and physical properties of many of them directly through their spectral emission and absorption features. Initial results from JADES produced detections of hundreds of galaxies at redshifts above 5, the epoch when the universe was less than 1 billion years old, and identified numerous candidates at even higher redshifts, including the record-breaking JADES GSZ 14-0. The survey is designed to build steadily over the lifetime of the mission, accumulating a rich database of galaxy properties across cosmic time that will underpin research for decades to come. The James Webb Space Telescope returned to one of astronomy's most iconic images, the Pillars of Creation in the Eagle Nebula, approximately 6,500 light-years from Earth, and captured it with a depth and clarity that revealed an entirely new dimension of activity within these towering columns of star-forming gas. In JWST's near-infrared view, the dense, dusty pillars that had appeared opaque and impenetrable in earlier Hubble images became partially transparent, allowing the telescope to reveal young stars embedded within the pillars themselves, some of them still surrounded by the disks of gas and dust from which their eventual planetary systems may one day form. The image also captured hundreds of newly formed stars in the surrounding region, their ruddy infrared light piercing through the clouds with a gentle glow that conveyed the quiet, sustained energy of ongoing stellar birth. The detailed MIRI mid-infrared view complemented this perspective, highlighting the warm molecular hydrogen gas that traces the boundaries between the pillars and the ionized gas surrounding them. The James Webb Space Telescope captured detailed images of Herbig-Haro objects, brilliant, narrow jets of material ejected by newborn stars as they actively gather surrounding material, revealing the intricate structure of these stellar birth announcements with unprecedented clarity. One particularly notable image captured a Herbig-Haro object known as HH212, showing a symmetrical pair of jets extending from a young star still embedded within its birth cloud, their edges glowing in vivid false-color hues that trace different temperatures and compositions of the shocked gas. These jets form when a young star ejects high-velocity streams of material along its rotation axis, and the shock waves created as those streams collide with the surrounding interstellar gas produce the glowing knots and arcs that characterize Herbig-Haro objects. JWST's ability to peer through the dusty envelopes surrounding young stars allowed it to observe these objects with a level of detail and completeness that ground-based or earlier space-based observations could not achieve. The James Webb Space Telescope captured a stunning view of the Rho-Ophiuchi cloud complex, the closest active star-forming region to our solar system at a distance of only about 390 light-years, revealing a richly detailed tapestry of young stellar objects and glowing gas that demonstrated the telescope's ability to examine the processes of stellar birth at close range. The image revealed approximately 50 young stars, many of them not significantly larger than our own Sun, surrounded by the warm glow of the gas and dust from which they are still forming, with some displaying the dark, elongated shadow features caused by edge-on disks of material around them. Jets from several of the young stars carved glowing red tunnels through the surrounding gas, their interaction with the interstellar medium producing the hydrogen emission that shines in deep crimson in the false color composite. The image was one of the first released as part of the telescope's first anniversary observations, chosen both for its visual beauty and for its scientific significance as a portrait of solar system formation in progress. The James Webb Space Telescope has observed numerous young stars surrounded by protoplanetary disks, flattened, rotating structures of gas and dust from which planets eventually form, probing the chemical and physical conditions that prevail in these planet-seed environments with infrared spectroscopy that can identify the molecular constituents within the disk material. Studies using MIRI have detected a wealth of molecular species within the inner regions of protoplanetary disks, including water, carbon dioxide, ethylene, and benzene-like aromatic molecules, providing a detailed inventory of the chemical building blocks available during the earliest stages of planet formation. These detections are particularly significant because they inform our understanding of how the chemical complexity of planetary systems like our own is assembled, and which organic molecules might be present on young planets from the very earliest moments of their formation. The ability to observe the chemistry of protoplanetary disks in detail is one of JWST's most productive contributions to the study of planetary system origins. The Tarantula Nebula, a vast star-forming region within the Large Magellanic Cloud, a satellite galaxy of the Milky Way located approximately 160,000 light-years from Earth, was among the early targets of the James Webb Space Telescope, which captured it in extraordinary detail across multiple infrared wavelengths. The region, also known as 30 Doradus, is one of the largest and most active star-forming nebulae known in the local group of galaxies, containing hundreds of thousands of stars at various stages of formation within a turbulent, multi-layered structure of gas, dust, and ionized plasma. The JWST images revealed thousands of never-before-seen young stars in the densest central region of the nebula, previously obscured behind thick curtains of dust that the telescope's infrared vision was able to penetrate. The chemical composition of the Tarantula Nebula's gas resembles that of star-forming regions in the distant young universe more closely than typical nearby nebulae, making it a valuable local laboratory for studying the conditions of cosmic star formation at an earlier era. The James Webb Space Telescope has proven exceptionally capable of detecting and characterizing brown dwarfs, objects that are more massive than planets but too small to sustain the nuclear fusion reactions that define true stars, within young star clusters, revealing populations of these cool, faint objects in far greater numbers than previous surveys had found. Within the Orion Nebula cluster alone, JWST detected a rich population of free-floating objects. At the boundary between planets and brown dwarfs, some with masses only a few times greater than Jupiter, floating independently through space without a parent star. Some of these objects were found in pairs, orbiting each other in wide binary configurations, a configuration referred to as planetary mass binary objects, that had not been observed in such numbers before and whose formation mechanism remains an intriguing open question. These discoveries are expanding our understanding of the lowest mass products of the star formation process and the blurry boundary between the smallest stars and the largest planets. As young massive stars form within molecular clouds, they emit powerful streams of radiation and stellar winds that compress and sculpt the surrounding gas, creating characteristic curved structures known as bow shocks where the stellar outflow meets denser surrounding material. The James Webb Space Telescope has captured these ephemeral features in remarkable detail in regions like the Orion Nebula, where the bright, hot young star Theta 1 Orionis C drives a powerful wind that creates bow shocks around smaller, cooler stars in its vicinity. These bow shocks are visible in JWST's infrared images as elegant curved arcs of glowing gas, their gentle curvature reflecting the balance between the pressure of the stellar wind pushing outward and the resistance of the denser ambient cloud material. The study of bow shocks and wind-driven structures provides valuable information about the energy budgets of young massive stars and the ways in which stellar feedback shapes the environment of star-forming regions. One of the most fundamental components of star-forming regions, and of the universe at large, is molecular hydrogen, two hydrogen atoms bound together into the simplest possible molecule, whose infrared emission lines fall squarely within the observational range of the James Webb Space Telescope's instruments. By mapping the emission of molecular hydrogen across star-forming nebulae, JWST has been able to trace the boundaries between hot, ionized gas regions and cooler, denser molecular gas, revealing the complex, layered structure of these environments with far greater detail than previous instruments could achieve. The mid-infrared capabilities of MIRI are particularly well suited for detecting pure rotational emission lines of molecular hydrogen, which arise from the cool layers of gas just beyond the reach of intense ultraviolet radiation from massive young stars. These maps of molecular hydrogen distribution have helped astronomers understand how the energy from young stars propagates through and eventually disperses the cloud material from which future generations of stars might otherwise form. The James Webb Space Telescope is uniquely positioned to trace the full life cycle of star-forming regions, from the dense, cold molecular cloud cores where gravitational collapse initiates stellar birth, through the luminous nebula phase where young massive stars illuminate and sculpt their birthplace, to the dispersal of cloud material that eventually returns enriched gas to the interstellar medium for future generations of stars. By observing star-forming regions across a range of ages, from very young, embedded clusters still surrounded by their birth material to older associations where the gas has been largely dispersed, JWST is building a comprehensive observational picture of how stellar nurseries evolve over millions of years. The telescope's ability to observe through the dense dust that conceals the youngest stages is particularly important, as it allows astronomers to see the very beginning of the sequence rather than only the later stages visible to optical instruments. The resulting body of observations is contributing to a more complete physical model of star formation that connects conditions in molecular clouds to the properties of the stellar populations they eventually produce. The James Webb Space Telescope captured a remarkable and visually striking phenomenon known as a light echo around the variable star V Aquila, a kind of stellar pulsator known as a Mira variable, in which pulses of light from the star's periodic brightenings propagate outward through surrounding shells of dust that the star has shed over thousands of years, illuminating them in expanding rings of reflected infrared light. Light echoes arise because light takes a finite time to travel from its source, meaning that a brief brightening event illuminates progressively more distant shells of dust in sequence, producing the appearance of an outward-moving ring even though the underlying shell structure itself is stationary. The JWST images of this phenomenon revealed nested concentric rings of glowing dust with extraordinary clarity, each ring corresponding to a different episode of material ejection from the aging star. These observations provide a uniquely elegant way to study the mass loss history of evolved stars and the structure of the dusty shells they build over their lifetimes. The James Webb Space Telescope has revolutionized the study of hot Jupiters, giant gas planets orbiting very close to their host stars, by capturing high-quality infrared spectra that reveal the chemical compositions of their atmospheres with a level of detail that previous instruments could not achieve. Hot Jupiters are ideal targets for atmospheric characterization because their large size and high temperatures produce strong spectral signatures, and their close orbits create frequent observational opportunities as they cross in front of and pass behind their host stars. JWST observations of hot Jupiters have detected molecules including water, carbon dioxide, carbon monoxide, methane, sulfur dioxide, and various other carbon and nitrogen-bearing species, building detailed chemical inventories that constrain models of atmospheric physics and chemistry. In some cases, the relative abundances of carbon and oxygen in the atmosphere provide information about where in the protoplanetary disk the planet originally formed, connecting the planet's present chemistry to its distant past. One of the early and scientifically significant discoveries from the James Webb Space Telescope was the detection of sulfur dioxide in the atmosphere of the hot Jupiter WSP-39b, a gas giant orbiting a Sun-like star approximately 700 light-years from Earth, representing the first clear detection of this molecule in an exoplanet atmosphere. The presence of sulfur dioxide is significant because it is believed to form through photochemical reactions, processes driven by the intense ultraviolet radiation from the host star, rather than simply being a thermochemical equilibrium product, meaning its detection provided the first direct evidence of photochemistry occurring in an exoplanet atmosphere. The JWST observations of WSP-39b were conducted as part of the early release science program and involved multiple instruments observing the planet's transit across its host star at different infrared wavelengths, building up a comprehensive spectrum from 0.6 to nearly 5 micrometers. The detection of sulfur dioxide demonstrated that JWST could not only identify atmospheric molecules but also reveal the photochemical processes shaping exoplanet atmospheres. Among the most anticipated targets for the James Webb Space Telescope are the 7 Earth-sized planets of the TRAPPIST-1 system, located approximately 40 light-years from Earth, where 3 of the 7 worlds orbit within the habitable zone of their small red dwarf host star. JWST has begun the detailed observational campaign needed to characterize the atmospheres of TRAPPIST-1 planets, an effort that requires many tens of hours of observation for each planet to accumulate sufficient signal-to-noise ratio to detect even thick secondary atmospheres. Early observations of TRAPPIST-1b and TRAPPIST-1c produced measurements of the planet's thermal emission, the infrared light they radiate from their dayside surfaces, that allowed astronomers to constrain the atmospheric properties of these worlds without relying on transmission spectroscopy. The results suggested that TRAPPIST-1c likely has little to no thick carbon dioxide atmosphere, an important finding that constrains models of volatile retention in planets orbiting active red dwarf stars. The James Webb Space Telescope achieved a landmark in the study of small, rocky exoplanets by detecting carbon dioxide in the atmosphere of 55 Cancri e, a super-Earth or lava world orbiting extremely close to its host star approximately 41 light-years from Earth, providing the first atmospheric detection on a planet smaller and denser than the gas giants that had previously dominated exoplanet atmospheric science. The detection was made using the thermal emission spectrum of the planet, measuring how its brightness changes at different infrared wavelengths as it passes behind and re-emerges from behind its host star, rather than through transmission spectroscopy during a transit. The presence of carbon dioxide and carbon monoxide in the planet's spectrum suggested a volatile-rich secondary atmosphere, one that may have been outgassed from a magma ocean covering much of the planet's surface. This result expanded the frontier of atmospheric characterization to include the smaller, denser rocky planets that are more similar to Earth in size and composition than the giant gas planets that had previously been the primary focus of exoplanet atmospheric studies. By monitoring the total infrared brightness of a planetary system continuously over the course of an entire orbit, a technique called phase curve observation, the James Webb Space Telescope can construct crude but informative maps of the temperature distribution across an exoplanet's surface or atmosphere, revealing the efficiency with which heat is transported from the dayside to the nightside. JWST has conducted phase curve observations of several hot Jupiters and smaller planets, measuring how the system's brightness varies as different portions of the planet rotate in and out of view, and then converting those brightness variations into temperature maps. On tidally locked planets, worlds that always show the same face to their host star, much as the Moon always shows the same face to Earth, the degree of dayside to nightside temperature contrast provides direct information about the strength and efficiency of atmospheric circulation. These phase curve datasets are among the most observationally demanding that JWST undertakes, but they provide uniquely holistic information about exoplanet climate systems that complements the chemical information provided by atmospheric spectroscopy. The primary method by which the James Webb Space Telescope studies exoplanet atmospheres is the transit technique, in which the telescope observes a planetary system as the planet passes in front of its host star from JWST's perspective, and the tiny fraction of starlight that filters through the planet's atmosphere at the planet's limb imprints the chemical fingerprints of atmospheric molecules onto the spectrum of the transmitted light. By comparing the spectrum of the star when the planet is not in transit to the spectrum during transit, Astronomers can isolate the contribution of the planet's atmosphere and identify the wavelengths at which specific molecules absorb or transmit infrared light. The same technique can be applied in reverse during a secondary eclipse, when the planet passes behind the star, to measure the planet's own emitted and reflected light, providing information about the planet's temperature and dayside chemistry. The James Webb Space Telescope's extraordinary infrared sensitivity and spectroscopic precision have made it by far the most capable instrument ever constructed for performing this type of exoplanet atmospheric characterization. In 2025, researchers analyzing James Webb Space Telescope spectroscopic data for the sub-Neptune exoplanet K2-18b, a world roughly 8.6 times the mass of Earth orbiting within the habitable zone of its red dwarf host star approximately 120 light-years away, announced tentative evidence for the presence of dimethyl sulfide in the planet's atmosphere, a molecule that on Earth is produced almost exclusively by marine phytoplankton. The detection was described as tentative and requiring additional confirmation, as the statistical significance was not sufficient to claim a definitive identification, but it prompted considerable and thoughtful scientific discussion about the interpretation of potential biosignature detections in a world where the atmospheric context differs profoundly from Earth's. The planet K2-18b was already known from previous JWST observations to show evidence for methane and carbon dioxide in its atmosphere, making it a candidate for a class of world called a Hycean planet, one with a hydrogen-rich atmosphere potentially overlying a liquid water ocean. These observations represent the frontier of JWST's exploration of atmospheric chemistry in potentially habitable worlds, a domain that will require patient accumulation of data and careful analysis in the years ahead. The James Webb Space Telescope is helping to characterize the remarkable diversity of exoplanet types that exist in our galaxy, from scorching hot Jupiters with dayside temperatures exceeding thousands of degrees to cold, distant ice giants, from super-Earths and sub-Neptunes that have no analog in our own solar system to small rocky worlds that may orbit within habitable zones around their host stars. This diversity is most powerfully investigated through spectroscopy, which allows JWST to measure the chemical compositions of atmospheres across a wide range of planetary sizes, temperatures, and orbital configurations, building up a comparative picture of how planetary atmospheres form, evolve, and are shaped by their host stars over billions of years. One of the emerging insights from JWST's exoplanet observations is the extraordinary variety of atmospheric compositions that exist even among planets of similar mass and size, suggesting that planetary formation and atmospheric evolution are highly sensitive to the specific conditions of each planetary system. This diversity provides a rich natural laboratory for testing theories of planetary formation and atmospheric physics that cannot be fully explored within our own solar system alone. Beyond observing planets that transit in front of their host stars, the James Webb Space Telescope is also capable of directly imaging some exoplanets, capturing photons of light emitted or reflected by the planet itself rather than inferring the planet's presence and properties indirectly through the effect on the host star's light. Direct imaging with JWST is possible for large, young planets orbiting at relatively large separations from their host stars, where the planet's own heat from recent formation makes it bright enough in infrared light to be distinguished from the surrounding glow of the host star using the telescope's coronagraphic capabilities. JWST has conducted direct imaging studies of several previously known directly imaged planets, capturing spectra of their atmospheres that reveal molecular compositions with greater detail than ground-based observations had achieved. The development of direct imaging as a complement to transit and secondary eclipse observations extends JWST's exoplanet atmospheric science to a broader population of planets than the transit technique alone can access. The James Webb Space Telescope's observations of sub-Neptune exoplanets, a class of worlds between Earth and Neptune in size that represents the most common type of planet found around other stars, are beginning to reveal the wide range of compositions and interior structures that these diverse objects can possess, including the possibility that some may be rich in water in proportions far exceeding anything found in our solar system. Theoretical models suggest that some sub-Neptunes may have thick layers of water in high-pressure forms, or deep global oceans beneath hydrogen-rich atmospheres, making them very different from the predominantly rocky terrestrial planets of our inner solar system. The spectroscopic capabilities of JWST are well suited to distinguishing between water-rich and water-poor sub-Neptunes by detecting the signatures of water vapor and other volatiles in their atmospheres, providing constraints on interior composition that complement the density measurements obtained from transit and radial velocity surveys. The emerging portrait of sub-Neptune diversity from JWST is illuminating one of the most fundamental questions in planetary science. How common are water-rich worlds, and what role does water play in determining the potential habitability of small planets? The James Webb Space Telescope turned its golden mirror toward our solar system's largest planet, Jupiter, and captured a pair of breathtaking infrared images that revealed the gas giant's complex atmospheric structure with a vivid clarity and detail that offered new perspectives on its swirling cloud systems. In JWST's near-infrared view, Jupiter's Great Red Spot, the enormous, centuries-old anticyclonic storm large enough to contain multiple Earths, appeared white because the high-altitude hazes above it reflect a great deal of near-infrared light, while the planet's equatorial zones and polar regions showed a rich tapestry of orange, yellow, and greenish amber tones corresponding to different altitudes and chemical compositions of cloud material. Auroras at both poles shone brilliantly in the near-infrared image, tracing the intense magnetic activity connecting Jupiter's magnetosphere to its upper atmosphere. The images also captured fine detail in several of Jupiter's smaller storms and the diffuse glow of its faint ring system, as well as two of its smaller moons, demonstrating JWST's ability to study solar system objects across a broad range of scales. The James Webb Space Telescope observed Saturn with its MIRI mid-infrared instrument, producing images that captured the planet and its iconic ring system in wavelengths that reveal temperature differences and compositional gradients that are invisible at shorter wavelengths. In MIRI's mid-infrared images, Saturn's disk appeared somewhat fainter than expected based on atmospheric models, a phenomenon that scientists are still investigating and that may relate to unexpected processes in the planet's stratosphere, while the rings appeared relatively brighter, illuminated by sunlight reflected from their icy particles. Seasonal changes in Saturn's upper atmosphere, driven by the planet's 29-year orbital period around the Sun and its significant axial tilt, were visible in the JWST data as subtle but measurable asymmetries between the northern and southern hemispheres. The telescope's ability to observe Saturn at multiple infrared wavelengths simultaneously provides a rich three-dimensional picture of the planet's atmospheric structure that complements the legacy datasets from the Cassini mission that ended in 2017. The James Webb Space Telescope captured a remarkably clear view of Neptune and its ring system, revealing the planet's thin rings in greater detail than any instrument since the Voyager 2 spacecraft flew past the ice giant in 1989, and providing the clearest image of Neptune's rings seen from Earth orbit. In JWST's near-infrared image, Neptune appeared quite different from the familiar blue color seen in Hubble's optical images. Instead, the methane-rich atmosphere absorbed much of the near-infrared light, giving the planet a somewhat muted, grayish tone, while bright streaks and patches of cloud activity were visible where high-altitude methane ice clouds reflected the sun's light. The planet's narrow rings appeared as thin, sharp arcs of reflected light surrounding the disk, and the bright spot of one of Neptune's moons, Triton, shone so prominently in the near-infrared that it cast a diffraction spike pattern in the image. The discovery that JWST could reveal Neptune's rings so clearly demonstrated its remarkable ability to image faint structures adjacent to bright objects even within our own solar system. The James Webb Space Telescope has provided new perspectives on Saturn's largest moon Titan, a world with a dense nitrogen-methane atmosphere and a landscape featuring lakes and seas of liquid methane and ethane, the only world in our solar system other than Earth with stable liquids on its surface. JWST's infrared observations penetrated through Titan's thick atmospheric haze to capture views of cloud activity in the Moon's atmosphere, including the detection of clouds near the Moon's northern hemisphere in images taken in 2022. These cloud detections were subsequently confirmed by ground-based telescopes, demonstrating that JWST's observations could be used to trigger rapid follow-up studies with other facilities when time-variable atmospheric phenomena were identified. The mid-infrared data from MIRI also provided new information about the composition and structure of Titan's atmosphere at different altitudes, adding to the comprehensive picture of this extraordinary world that was built up during the Cassini mission. The James Webb Space Telescope has observed several comets, icy remnants of the early solar system that preserve the composition of the primordial material from which the planets formed, providing new insights into their chemical inventories and the processes by which volatile materials are released into space as comets approach the Sun. JWST's observations of comets have detected a variety of carbon-bearing and oxygen-bearing molecules in cometary comae, the diffuse envelopes of gas and dust surrounding the comet's nucleus, including carbon dioxide, carbon monoxide, and ethane, building a detailed picture of the chemical complexity preserved in these ancient objects. The detection of carbon dioxide in particular, which cannot be observed from the ground because the Earth's own atmosphere absorbs those infrared wavelengths, has been a significant contribution of JWST to cometary science, as carbon dioxide is one of the most abundant molecular ices in comets but had previously been very difficult to measure from space-based observatories with the required sensitivity. By comparing the chemical compositions of different comets, JWST is helping to map the compositional gradient of the early solar system that shaped the distribution of materials available to the forming planets. The James Webb Space Telescope has turned its spectroscopic instruments towards some of the asteroids of the main belt that lies between Mars and Jupiter, probing the surface compositions of these rocky and sometimes icy remnants of the early solar system with infrared spectra that reveal the mineral and organic chemical content of their surfaces. Hydrated minerals, silicates that contain water molecules chemically bound within their crystal structure, have been identified on several asteroids in JWST spectra, providing direct evidence that water was present and chemically active in the asteroid belt during the early solar system. The detection of complex organic molecules, including carbonates and aromatic compounds, on the surfaces of some carbonaceous asteroids complements findings from sample return missions and meteorite studies, building a more complete picture of the chemical processes that operated in the early solar nebula. Understanding the composition and diversity of asteroids is important not only for reconstructing the history of our solar system, but also for understanding the delivery of water and organic materials to the early Earth, which may have contributed to the conditions that allowed life to emerge. The James Webb Space Telescope has observed Mars with both NIRCam and MIRI, capturing spectra of the Martian atmosphere that probe the distribution of carbon dioxide, dust, and water vapor as a function of altitude and local time, adding a global synoptic perspective to the highly detailed but spatially localized measurements being made by rovers and orbiters at the planet's surface. In the near-infrared images, the dark and light surface regions of Mars were clearly visible, as were the polar ice caps and some of the planet's largest geological features, while the mid-infrared data revealed thermal emission from the planet's surface and dust-laden atmosphere. JWST's ability to observe Mars at multiple infrared wavelengths simultaneously provides a snapshot of the planet's atmospheric state across a wide vertical range, from the surface up through the stratosphere, complementing the in-situ measurements being made by the Curiosity and Perseverance rovers in Gale Crater and Jezero Crater respectively. These observations demonstrate JWST's capacity as a synoptic observer of solar system atmospheres, providing a valuable global context for the local measurements being accumulated by surface missions. The James Webb Space Telescope made an intriguing discovery related to a main-belt comet, an object that orbits within the asteroid belt like a typical asteroid but displays cometary activity such as a dust coma or tail when it passes closer to the Sun, providing new clues about the presence of water ice in the inner solar system. Observations of the object 238P Reid revealed the presence of a clear water vapor coma around the comet, confirming that water ice can persist within the asteroid belt close enough to the Sun to be occasionally sublimated into gas. This detection was scientifically significant because it provided direct observational confirmation of a theoretical prediction that some main-belt asteroids can harbor water ice at shallow depths beneath their surfaces, protected from evaporation by a thin regolith layer. The finding adds to the evidence that the water delivered to the early Earth may have partly originated from objects in the inner solar system rather than exclusively from the outer solar system as some models suggest. Among the solar system observations conducted by the James Webb Space Telescope were mid-infrared observations of Io, Jupiter's innermost large moon and the most volcanically active body in the solar system, whose intense geological activity is driven by the powerful tidal forces exerted by Jupiter and its other large moons. JWST's MIRI instrument captured thermal emission from Io's surface, revealing the distribution of volcanic heat sources across the moon's hemisphere as bright, warm patches against the cooler background of surrounding terrain. The mid-infrared images highlighted several active volcanic sites, including the persistent and enormously productive Loki Patera, a lava lake hundreds of kilometers across, and the intense, towering plumes of several volcanic centers that have been active for decades. These JWST observations provide a new vantage point on Io's volcanism that complements the detailed observations made by the Juno spacecraft, which has been orbiting Jupiter since 2016 and making periodic close approaches to the Moon. Looking toward the outer reaches of our solar system, the James Webb Space Telescope has begun observations of Kuiper Belt objects, the ancient icy bodies that populate the outer solar system beyond Neptune's orbit, probing their surface compositions with mid-infrared spectroscopy to understand the primordial material from which they formed in the cold, distant reaches of the early solar nebula. The infrared spectra of Kuiper Belt objects can reveal the presence of methanol, methane, water ice, carbon dioxide ice, and complex organic compounds known as tholins, reddish substances produced when simple molecules like nitrogen and methane are irradiated by cosmic rays or solar ultraviolet light over billions of years. These spectral signatures provide clues to the conditions of temperature and radiation environment in the outer solar nebula during the era of planet formation, preserving a chemical record that is unavailable from the more processed and altered surfaces of the inner solar system's rocky bodies. JWST's observations of Kuiper Belt objects are beginning to build a systematic compositional survey of these ancient archives, contributing to our understanding of the chemical conditions that prevailed at the outermost edges of our planetary system's formation. The James Webb Space Telescope captured a stunning view of the Cartwheel Galaxy, a ring galaxy located approximately 500 million light-years from Earth in the constellation Sculptor, revealing in unprecedented infrared detail the aftermath of a high-speed collision between two galaxies that occurred hundreds of millions of years ago. The collision sent a shockwave rippling outward through the larger galaxy's disk like a stone dropped into a calm pond, triggering bursts of star formation along an expanding ring of material that gives the cartwheel its characteristic wagon wheel appearance. JWST's NIRCam image revealed thousands of young star clusters arranged along this ring, their blue-white light contrasting with the warm amber glow of older stellar populations in the galaxy's central region. The MIRI mid-infrared data complemented this view by highlighting the distribution of warm dust, heated by the intense star formation activity, and the complex filamentary structure of the spokes connecting the outer ring to the inner core. The James Webb Space Telescope observed the Antennae galaxies, a pair of spiral galaxies in the process of merging, located approximately 60 million light-years away in the constellation Corvus, revealing the distribution of star formation and warm dust in these interacting systems with infrared sensitivity that penetrates through the heavy obscuration that makes the most active star-forming regions invisible in optical light. As the two galaxies have interpenetrated and their respective disk structures have been disrupted by mutual gravitational forces, enormous clouds of molecular gas have been compressed by the collision, triggering intense bursts of star formation in regions that are so heavily dust-enshrouded that visible light observations see only a tiny fraction of the new stars being born. JWST's infrared vision revealed a rich population of compact star-forming regions and young star clusters distributed throughout the merger zone, many of them deeply embedded within dust clouds that appear completely opaque in Hubble Space Telescope images. The Antennae system serves as one of the most well-studied nearby examples of the major galaxy mergers that were far more common in the early universe. When galaxies interact through gravitational encounters, they can draw out long, graceful streamers of stars and gas called tidal tails, which extend for hundreds of thousands of light-years into intergalactic space and preserve a record of the gravitational dynamics of the interaction. The James Webb Space Telescope has captured these delicate structures in several interacting galaxy systems with exceptional clarity, revealing the distribution of stars, star clusters, and ionized gas within tidal tails with a level of detail that allows astronomers to reconstruct the orbital histories of the merging systems. Some tidal tails contain compact knots of star formation, sometimes called tidal dwarf galaxies in formation, where gas compressed by tidal forces has accumulated and begun forming new stars, potentially contributing to the population of small satellite galaxies that surround large systems. The graceful curving forms of tidal tails, rendered in warm infrared hues, are among the most visually striking products of galaxy interactions and provide a vivid demonstration of the power of gravity to reshape the largest structures in the universe over cosmic timescales. The James Webb Space Telescope has studied several compact groups of galaxies, relatively tight configurations of 3 to 10 galaxies that are physically close enough to one another to be interacting gravitationally, providing new insights into how galaxy evolution is accelerated by the dense environments of these miniature cosmic neighborhoods. In compact groups, the close proximity of galaxies means that tidal interactions are frequent and intense, stripping gas from individual galaxies into a diffuse intragroup medium, triggering or quenching star formation depending on the local conditions, and gradually leading to the merger of group members into a single, larger elliptical galaxy over billions of years. JWST's mid-infrared observations are particularly useful for studying compact groups because they can detect the warm dust emission associated with star formation even in galaxies that are heavily obscured by the gas and dust stirred up by tidal interactions. The detailed portrait of galaxy group environments provided by JWST contributes to understanding how a galaxy's surroundings shape its evolution throughout cosmic history. The James Webb Space Telescope has observed elliptical galaxies, the smooth, featureless systems that represent the end state of major galaxy mergers, in both the nearby and distant universe, probing the stellar populations within them and the remnants of any star formation or nuclear activity that may have accompanied the merging events that created them. Elliptical galaxies are dominated by old, red stellar populations and typically show little ongoing star formation, but JWST's sensitivity allows it to detect the faint glow of any remaining warm dust or ionized gas within them, traces of the dying embers of star formation or the residual activity of the central black hole. Some massive elliptical galaxies are surrounded by extended stellar halos, built up from multiple merging events over billions of years, whose spatial extent and surface brightness profiles can be measured with JWST's deep imaging capabilities. The study of nearby massive ellipticals provides a template for understanding the massive quiescent galaxies that have been observed at high redshifts, connecting the archaeology of ancient stellar populations in the local universe to the observational history of galaxy formation seen at large look-back times. The large-scale structure of the universe is organized into a vast cosmic web of filaments, sheets, and nodes, with galaxies and galaxy clusters preferentially forming at the intersections of dark matter filaments where gas is concentrated by the combined gravitational pull of the surrounding structure. The James Webb Space Telescope is beginning to reveal the cosmic web directly through deep-field imaging that captures the faint emission of gas in the voids and filaments between galaxies, as well as by identifying and mapping the three-dimensional distribution of galaxies in deep fields through spectroscopic redshift surveys. Some JWST observations have captured dense galaxy overdensities at high redshift, protoclusters in the process of forming, that represent the earliest visible nodes of the cosmic web, regions where the first large-scale structures were assembling from the diffuse gas of the early universe. The ability to directly observe the large-scale structure of the universe in the infrared at high redshifts is one of the most powerful tools JWST brings to cosmological research, complementing the statistical measurements of the cosmic microwave background and the clustering of galaxies across cosmic time. As galaxies move through the dense environments of galaxy clusters, gravitational interactions between cluster members can strip stars from their outer regions, gradually building up a diffuse, extremely faint glow of intracluster light that permeates the space between the cluster's member galaxies like a softly luminous cosmic fog. The James Webb Space Telescope's extraordinary sensitivity and stability have made it one of the best instruments ever constructed for detecting and studying this intracluster light, which can represent up to 20 or 30% of the total stellar light in a galaxy cluster, but is so diffuse that it was long considered nearly impossible to measure accurately. By analyzing the colors and spatial distribution of the intracluster light, astronomers can infer the ages and metallicities of the stripped stellar populations, providing information about the histories of the galaxies that contributed them and the timescale over which the cluster has been assembling. JWST observations of galaxy clusters at intermediate and high redshifts are beginning to extend the study of intracluster light to earlier epochs, tracing the assembly history of these massive structures through their scattered stellar remains. One of the central unresolved questions in galaxy evolution is how and why some galaxies, particularly massive ones, cease forming new stars and transition from actively star-forming blue galaxies to passively evolving red ones, a process called quenching. The James Webb Space Telescope is contributing to this question by observing galaxies in the process of quenching at various redshifts, capturing the transition between active and passive states with infrared diagnostics that can identify the presence of both residual star formation and the feedback processes, from central black holes or powerful stellar winds, that may be responsible for halting it. Some high redshift massive galaxies observed by JWST appear to have quenched their star formation surprisingly early in cosmic history, within the first 2 billion years after the Big Bang, challenging models that predicted such rapid quenching would be uncommon. The physical mechanism responsible for quenching remains an active area of investigation, with JWST's detailed spectroscopic observations of quenching and recently quenched galaxies providing new constraints on the relative importance of different proposed mechanisms. Among the populations of galaxies that the James Webb Space Telescope is revealing for the first time are those that are extremely luminous in the infrared but largely invisible in optical light because they are entirely enshrouded in dust, objects that absorbed and re-radiated essentially all of their starlight or AGN emission as infrared radiation. These dust-obscured galaxies were known to exist from previous infrared satellite missions such as Spitzer and Herschel, but could rarely be studied in detail because those missions lacked the resolution to separate them from neighboring sources and the spectroscopic sensitivity to characterize their properties. JWST's combination of high angular resolution, deep sensitivity, and powerful infrared spectrographs has enabled systematic studies of dust-obscured galaxies at a range of redshifts, revealing the physical conditions, star formation rates, and black hole activity within some of the most productive but previously hidden systems in the universe. Some of these newly characterized dust-obscured galaxies at high redshift appear to be among the most massive and rapidly evolving systems of their epoch, suggesting that significant portions of the early universe's most vigorous evolution have been hidden from optical surveys. The James Webb Space Telescope has peered through the thick veil of dust and gas that obscures the central regions of our own Milky Way galaxy, capturing infrared images and spectra of the complex stellar populations, molecular clouds, and active processes that characterize the galactic center region surrounding the supermassive black hole Sagittarius A star. The galactic center is an environment of extraordinary density and activity, with a stellar population thousands of times denser than the solar neighborhood, powerful magnetic fields, and supernova remnants and ionized gas structures that reflect the tumultuous history of the region. JWST's NIRCam images of the galactic center have revealed thousands of previously unknown stars in the dense inner regions, many of them massive and luminous young stars whose formation in such a turbulent environment provides intriguing clues about the conditions that allow star formation to proceed near a supermassive black hole. The mid-infrared MIRI observations complement these near-infrared views by tracing the warm dust emission from molecular clouds and the complex filamentary structures of ionized gas that radiate away the energy injected by stellar winds and supernova explosions. The James Webb Space Telescope has observed quasars, the luminous cores of galaxies powered by rapidly accreting supermassive black holes, across a wide range of cosmic epochs, from the nearby universe to the very edges of observable space, probing how these extraordinary energy sources and their host galaxies co-evolved across the history of the cosmos. At high redshifts, JWST's infrared sensitivity has enabled spectroscopic observations of quasars whose host galaxies are ordinarily overwhelmed by the brilliance of the central source, providing the first measurements of stellar populations and morphologies in some of the most distant known quasar host systems. The spectra of distant quasars observed by JWST reveal the emission lines of highly ionized gas surrounding the central black hole, as well as absorption features from intervening clouds of intergalactic gas that the quasar light passes through on its long journey to the telescope. By studying the properties of quasars and their host galaxies across cosmic time, JWST is contributing to our understanding of the connection between black hole growth and galaxy evolution, one of the central themes of modern astrophysics. The James Webb Space Telescope is contributing to measurements of the masses of supermassive black holes at the centers of nearby galaxies by observing the dynamics of gas and stars in the innermost regions of galactic nuclei, where the gravitational influence of the central black hole dominates the motion of surrounding material. JWST's NIR-SPEC integral field unit, a mode that captures a spectrum for every point within a two-dimensional area on the sky simultaneously, is particularly well suited for these dynamical measurements, allowing astronomers to map the velocity of ionized gas as a function of position across the central region of a galaxy and model the gravitational potential required to produce the observed motions. These measurements are important for refining the empirical correlations between black hole mass and the properties of the host galaxy's central bulge, correlations that encode the history of coevolution between black holes and their host systems. Accurate black hole mass measurements in a diverse sample of galaxies across a range of masses and environments are essential for testing theoretical models of black hole formation and growth. One of the surprising discoveries emerging from early JWST deep field observations was the identification of a population of compact, red objects that appear in deep infrared images as tiny, unresolved points of warm-colored light, informally nicknamed the little red dots, whose nature required careful spectroscopic investigation to determine. Spectroscopic follow-up of these objects revealed that many of them are broad-line active galactic nuclei, galaxies with rapidly accreting central black holes whose broad emission lines indicate very high-velocity gas in the immediate vicinity of the black hole, at relatively high redshifts corresponding to the universe's first 2 to 3 billion years. What made the little red dots scientifically intriguing was the apparent tension between the large black hole masses implied by their broad emission lines and the relatively faint or compact host galaxies in which they appear to reside, suggesting that in some systems the black hole may have grown to significant mass before the surrounding galaxy had fully assembled. This population of high redshift broadline AGN represents a previously underappreciated channel of early black hole and galaxy coevolution that JWST has uniquely enabled the study of. One of the central questions in galaxy evolution concerns the ways in which energy and material released by an active galactic nucleus, the luminous, accreting black hole at a galaxy's center, can influence or regulate the surrounding galaxy's star formation, a process known as AGN feedback. When a supermassive black hole is actively accreting, it can release enormous amounts of energy in the form of radiation, winds, and jets that heat, accelerate, or expel the gas from which new stars would otherwise form, potentially shutting down star formation across the entire galaxy. The James Webb Space Telescope is providing detailed observations of AGN feedback in action, capturing the emission line signatures of fast-moving, AGN-driven outflows of gas in galaxies at various stages of this process, allowing astronomers to measure the mass outflow rates and energetics of feedback across a range of black hole masses and host galaxy properties. These measurements are essential for testing the theoretical models of AGN feedback that are incorporated into numerical simulations of galaxy formation and for understanding whether black hole-driven feedback is indeed responsible for quenching star formation in massive galaxies. Some actively accreting supermassive black holes produce narrow, highly collimated jets of material that extend from the galactic nucleus outward for distances that can span millions of light-years into the surrounding intergalactic medium, carrying energy and magnetic fields far beyond the boundaries of the host galaxy. The James Webb Space Telescope has observed the infrared emission from jets in nearby active galaxies, capturing the warm dust emission heated by the jet's interaction with surrounding gas and the synchrotron radiation from relativistic electrons spiraling along the jet's magnetic field lines at wavelengths that complement radio observations from other facilities. In some systems, JWST's high angular resolution has allowed the mapping of the jet's interaction with the host galaxy's interstellar medium, revealing the regions where the jet's energy is being deposited and potentially influencing the surrounding gas. The ability to observe jet-host galaxy interactions across multiple wavelengths and scales is essential for understanding how the energy carried by jets is thermalized and distributed through the surrounding medium, one of the key physical processes in AGN feedback. When the James Webb Space Telescope captures a spectrum of an active galactic nucleus, it records a rich and information-dense collection of emission lines, absorption features, and continuum radiation that collectively reveal the physical conditions, chemical composition, kinematics, and ionization state of the gas surrounding the accreting black hole across a range of distances from the central source. The broad emission lines that characterize Type 1 AGN, those where the central engine is viewed directly rather than through an obscuring torus of dust, arise from gas moving at thousands of kilometers per second in the immediate vicinity of the black hole, their widths directly encoding the velocity dispersion of this fast-moving gas. Narrower emission lines from more distant, slower-moving gas encode information about the chemical enrichment and ionization conditions of the host galaxy's interstellar medium in the regions surrounding the nucleus. By analyzing these spectral features in detail, JWST is building comprehensive physical models of AGN across a wide range of luminosities, redshifts, and host galaxy properties that are advancing our understanding of how these powerful energy sources interact with their environments. The James Webb Space Telescope is being used for a sophisticated technique called reverberation mapping, in which the time delay between variations in the luminosity of an AGN's continuum radiation and the corresponding response in its broad emission lines is used to measure the size of the region from which those emission lines arise, and ultimately to constrain the mass of the central black hole. Because light travels at a finite speed, the ionized gas clouds surrounding the black hole, the broad line region, respond to changes in the ionizing radiation from the accretion disk after a delay that corresponds to the light travel time between the disk and the gas clouds. By measuring this delay through careful monitoring of the AGN's variability at multiple wavelengths over many epochs, Astronomers can infer the physical radius of the broadline region and combine it with the velocity of the gas, measured from the width of the emission lines, to estimate the black hole mass. JWST's infrared sensitivity extends reverberation mapping to AGN at higher redshifts and in more heavily obscured environments than were accessible to optical monitoring campaigns, opening new windows on the black hole mass function across cosmic time. As galaxies merge, their central supermassive black holes eventually sink toward each other through dynamical friction and begin orbiting each other as a gravitationally bound binary pair, a process that may ultimately lead to the emission of gravitational waves when the two black holes finally coalesce. The precursor to this final coalescence is the dual AGN phase, in which both black holes in a merging galaxy pair are actively accreting and luminous, appearing as two distinct sources of infrared emission within the combined galaxy. The James Webb Space Telescope's high angular resolution in the infrared makes it an excellent tool for identifying dual AGN systems at intermediate separations, those that are close enough to be within a single galaxy but far enough apart to be spatially resolved, that represent an important stage in the long process of binary black hole formation and merger. Identifying and characterizing dual AGN populations across a range of galaxy merger stages and redshifts is an important contribution to understanding the role of galaxy mergers in driving black hole growth and the production of gravitational wave sources. When a star wanders too close to a supermassive black hole and is torn apart by tidal forces, the resulting debris stream can briefly power a luminous transient known as a tidal disruption event, in which roughly half the stellar material falls back onto the black hole over weeks to months and generates a flare of electromagnetic radiation spanning from X-rays to infrared wavelengths. The James Webb Space Telescope has observed the infrared emission from several tidal disruption events, probing the dust that is heated and illuminated by the central flare in regions around the black hole where the interstellar medium has been enriched by the debris of previous stellar encounters. The infrared echo of a tidal disruption event, the re-radiation by surrounding dust of the optical and ultraviolet radiation produced by the accretion flare, provides information about the distribution and composition of dust in galactic nuclei that is difficult to measure by other means. JWST's sensitivity to these dust echoes has opened a new window on the environments of quiescent supermassive black holes by illuminating them with the light of transient accretion events. The standard unified model of active galactic nuclei proposes that many different observational classes of AGN, including Seyfert galaxies, quasars, blazars, and radio galaxies, are fundamentally the same type of object viewed from different angles relative to an obscuring torus of dust and gas surrounding the central accretion disk, with the observed differences arising primarily from orientation effects rather than intrinsic differences in the underlying physics. The James Webb Space Telescope is contributing to tests of this unified model by observing AGN in the mid-infrared, where emission from the warm dust of the obscuring torus dominates, allowing direct measurement of the torus's properties, its size, temperature distribution, geometry, and covering fraction, in a range of AGN types and luminosities. MIRI spectroscopy of AGN at various redshifts and luminosities is building a statistical picture of how torus properties scale with AGN power and environment, testing predictions of the unified model and revealing cases where the simple orientation-based explanation breaks down. The results contribute to a more nuanced understanding of AGN structure in which both orientation and intrinsic differences in black hole mass, accretion rate, and host galaxy properties play roles in determining the observed characteristics of any given active nucleus. One of the most powerful capabilities of the James Webb Space Telescope is its ability to identify specific molecules through their infrared spectral fingerprints, the characteristic patterns of absorption and emission at precise wavelengths that each molecular species produces when interacting with infrared light. Every molecule vibrates and rotates in ways that depend on its specific atomic composition and bonding structure, and these molecular motions produce spectral features at predictable wavelengths that serve as unique identifiers, much as a fingerprint identifies an individual. JWST spectrographs cover a broad range of infrared wavelengths with high spectral resolution, allowing them to identify dozens of molecular species simultaneously in a single spectrum of a planetary atmosphere, stellar outflow, or interstellar cloud. The resulting molecular inventories are transforming our understanding of the chemistry occurring in every type of astrophysical environment, from the frozen surfaces of solar system objects to the turbulent disks around newly forming stars to the atmospheres of planets in other solar systems. Water, the simple molecule composed of 2 hydrogen atoms and 1 oxygen atom that is essential for life as we know it, has been detected by the James Webb Space Telescope in a remarkable variety of astrophysical environments, from the atmospheres of exoplanets to the protoplanetary disks surrounding young stars to the cometary comae of solar system objects. The detection of water vapor in the inner regions of protoplanetary disks by MIRI spectra has provided new insights into how water is distributed within planet-forming environments, confirming that significant water reservoirs are present in the planet formation zones of young stellar systems. On exoplanets, JWST has detected water vapor in the atmospheres of several hot Jupiters and sub-Neptunes, building a growing statistical picture of how common water-bearing atmospheres are among planets of different sizes, temperatures, and orbital configurations. The pervasive presence of water across so many different cosmic environments reinforces the view that the chemical preconditions for life as we understand it may be widely distributed throughout the galaxy. Carbon, the 4th most abundant element in the universe by mass, forms the backbone of an extraordinarily diverse family of molecules in space, from simple diatomic species like carbon monoxide to large aromatic structures called polycyclic aromatic hydrocarbons. And the James Webb Space Telescope's infrared capabilities are providing new windows on the richness and distribution of this cosmic carbon chemistry. Polycyclic aromatic hydrocarbons, large flat molecules consisting of fused rings of carbon atoms with hydrogen atoms at their edges, are among the most abundant carbon-bearing molecules in the interstellar medium, and their characteristic infrared emission features at several key wavelengths are prominently detected by JWST's instruments in a wide range of environments including star-forming regions, galaxies, and even the disks around young stars. MIRI spectra have revealed the presence of complex organic molecules including acetylene, benzene, and ethane in the inner regions of protoplanetary disks, species that represent important steps on the chemical pathway from simple interstellar molecules toward the complex organic compounds found in meteorites and comets. This expanding inventory of complex carbon chemistry in space is deepening our understanding of the chemical richness that pervades the universe and provides the raw materials from which the chemistry of life ultimately arises. The James Webb Space Telescope's observations of molecular clouds and protostellar systems are contributing new insights into the chemical processes by which simple interstellar molecules, hydrogen, carbon monoxide, water, and nitrogen, are converted into the more complex organic species that have been found in meteorites, comets, and the atmospheres of planetary bodies. Chemical reactions in the icy mantles of interstellar dust grains, driven by cosmic ray irradiation and ultraviolet photons, can produce complex molecules including glycolaldehyde, methyl formate, and various amino acid precursors even in the cold, dark depths of molecular clouds where temperatures hover around 10 degrees above absolute zero. As a protostar forms and heats its surrounding envelope, the evaporation of these ice mantles releases the accumulated organic molecules into the gas phase, where they can be detected through their infrared spectral signatures by JWST's instruments. The progression from simple atomic species to complex organic molecules in astrophysical environments represents the first steps in the long chemical journey from the Big Bang's hydrogen and helium to the molecular complexity of living systems. All elements heavier than hydrogen and helium, including carbon, oxygen, nitrogen, iron, calcium, and every other element that makes up the planets and living things, were forged in the interiors of stars through the process of nuclear fusion and then dispersed into the interstellar medium through stellar winds and the explosive deaths of massive stars. The James Webb Space Telescope observes the aftermath of these elemental creation events in several ways, including measuring the elemental abundances in the spectra of galaxies across cosmic time to trace how the universe's chemical composition has evolved from the near-pristine hydrogen and helium of the Big Bang toward the chemically rich environments of today. In star-forming regions, JWST spectra reveal the products of stellar nucleosynthesis already mixed into the gas and dust from which new stars and planetary systems are forming, demonstrating how each generation of stars enriches the interstellar medium for the next. The oxygen, carbon, iron, and other elements that JWST detects in distant galaxies, protoplanetary disks, and cometary atmospheres were all created in the interiors of previous generations of stars, a cosmic genealogy connecting every astronomical observation to the physical processes operating in stellar interiors. The James Webb Space Telescope has conducted systematic surveys of the ice composition on the surfaces of dust grains within cold molecular clouds, capturing the infrared absorption features produced when infrared light from background sources passes through the icy grains and is partially absorbed at wavelengths corresponding to the vibrational modes of specific molecular ices. The resulting surveys have detected a rich variety of molecular ices including water, carbon dioxide, ammonia, methane, methanol, carbonyl sulfide, and various other simple and complex species, building the most comprehensive inventory of interstellar ice composition ever assembled. These ices represent the solid phase reservoir of volatile molecules that will eventually be incorporated into the comets, asteroids, and planetary bodies forming in any protoplanetary disk that develops from the cloud material. The comparative study of ice composition in molecular clouds of different ages, masses, and radiation environments is revealing how interstellar chemistry varies with physical conditions, providing a foundation for understanding the chemical starting conditions of planetary system formation. By measuring the strength of oxygen emission lines in the spectra of galaxies at a range of redshifts, the James Webb Space Telescope is tracing the cosmic history of oxygen enrichment, the process by which successive generations of massive stars produced oxygen in their interiors and dispersed it into the interstellar medium through stellar winds and supernova explosions. Oxygen is among the most important elements for both stellar evolution and for the chemistry of planetary atmospheres and the origins of life, and its abundance relative to hydrogen in a galaxy's gas phase interstellar medium serves as a sensitive tracer of the galaxy's star formation history and the degree to which evolved stellar material has been recycled into the interstellar medium. JWST's spectroscopic observations of high-redshift galaxies have revealed that many early galaxies had significantly lower oxygen abundances relative to hydrogen than galaxies in the present-day universe. As expected, if the chemical enrichment of galaxies builds up progressively over cosmic time, but some appear to have been enriched more rapidly than simple models predict. These measurements of oxygen abundances across cosmic time provide a quantitative test of our understanding of how galaxies accumulate and distribute the chemical products of stellar evolution. Phosphorus is one of the 6 elements considered essential to life as we know it, alongside carbon, hydrogen, nitrogen, oxygen, and sulfur. Yet it is one of the least understood in terms of its formation and distribution in the interstellar medium, partly because its most accessible spectral features are difficult to observe from the ground. The James Webb Space Telescope's infrared capabilities are beginning to provide new constraints on phosphorus-bearing molecules in space, including potential contributions from observations of molecular clouds and protostellar systems where phosphorus-bearing species may be present in icy grain mantles. Understanding where phosphorus is concentrated in the interstellar medium and how it is incorporated into planetary systems is important for assessing the conditions under which the chemistry of life can potentially develop on young planets. The broader effort to inventory all 6 biologically essential elements across a range of astrophysical environments, from the molecular clouds that birth new stars to the planetary disks in which worlds form, is one of the long-term scientific contributions that JWST is uniquely positioned to make. The dust produced by evolved stars, particularly the asymptotic giant branch stars that are among the most prolific dust producers in the galaxy, contains a rich variety of mineral grains and amorphous silicate particles whose mid-infrared spectral signatures are elegantly captured by the James Webb Space Telescope's MIRI spectrograph. By analyzing these dust emission features, astronomers can determine the mineralogical composition of circumstellar dust, distinguishing between silicate and carbonaceous grain species, identifying crystalline versus amorphous grain structure, and measuring the size distribution of dust particles, all of which reflect the temperature, pressure, and chemical conditions prevailing in the stellar atmospheres where the grains condensed. The properties of circumstellar dust are scientifically important not only for understanding the physical processes in stellar outflows but also because this stellar dust represents one of the primary sources of newly formed solid material that is injected into the interstellar medium and eventually incorporated into the next generation of planetary systems. JWST's detailed characterization of circumstellar dust chemistry in evolved stars of various masses and compositions is building a comprehensive picture of the solid-phase chemical legacy that dying stars bequeath to the interstellar medium. The interstellar medium is far from the empty, featureless void that it might appear in visible light photographs. It is instead a richly populated chemical environment containing hundreds of different molecular species that have been identified through their radio, infrared, and millimeter-wave spectral signatures, ranging in complexity from simple diatomic molecules like hydrogen fluoride and carbon monoxide to elaborate structures like Buckminster fullerene and various chiral organic molecules. The James Webb Space Telescope is contributing to this molecular zoo by detecting and characterizing species that are particularly well suited to infrared observation, especially those involving vibrational modes of molecules containing carbon-hydrogen, oxygen-hydrogen, and carbon-oxygen bonds, in environments ranging from dense molecular cloud cores to the outflows of evolved stars to the atmospheres of exoplanets. Some of the species detected in space are among the most complex organic molecules known to exist outside of laboratory or biological settings, suggesting that chemical evolution toward complexity can proceed remarkably far from the conditions of any planetary surface. The steadily expanding inventory of molecular species in space provides a constantly deepening appreciation of the chemical richness of the cosmos and the many-stepped pathway from simple elements to complex molecular structures. One of the most compelling puzzles in modern cosmology is the Hubble tension, a persistent and growing discrepancy between two independently derived measurements of the rate at which the universe is expanding, known as the Hubble constant. Measurements based on the cosmic microwave background radiation and the standard cosmological model consistently yield a Hubble constant of approximately 67 to 68 kilometers per second per megaparsec, while measurements based on the local distance ladder, using Cepheid variable stars and Type Ia supernovae as standard candles to measure distances to nearby galaxies, consistently give a higher value of approximately 73 kilometers per second per megaparsec. The James Webb Space Telescope has contributed to this investigation by providing new, highly precise measurements of Cepheid variable stars in several nearby galaxies, allowing a careful reassessment of the critical first rungs of the cosmic distance ladder with reduced systematic uncertainties. While JWST's results have largely confirmed the measurements made previously with the Hubble Space Telescope rather than resolving the tension, they have placed the discrepancy on a firmer observational footing and sharpened the scientific case that the tension may reflect new physics beyond the standard cosmological model. The cosmic microwave background, the faint, uniform glow of thermal radiation that pervades the entire sky and represents the cooled afterglow of the hot, dense plasma that filled the universe approximately 380,000 years after the Big Bang, provides the cosmological context within which all of the James Webb Space Telescope's observations of galaxies, stars, and exoplanets must be interpreted. The temperature fluctuations imprinted on the cosmic microwave background at the level of roughly 1 part in 100,000 encode the density fluctuations of the early universe that seeded all subsequent structure formation, and the statistical properties of these fluctuations are exquisitely well measured by satellite missions like Planck. The standard cosmological model derived from the cosmic microwave background predicts the abundance of dark matter, the density of dark energy, the geometry of the universe, and the timeline of large-scale structure formation, all parameters against which JWST's observations of the high redshift universe can be compared. The interplay between the early universe constraints provided by the cosmic microwave background and the late universe observations provided by JWST is one of the most powerful tools available for testing and refining our cosmological framework. Dark matter, the invisible, gravitationally influential substance that makes up approximately 27% of the total energy density of the universe but emits no detectable electromagnetic radiation, makes its presence felt primarily through its gravitational effects on visible matter and light, and the James Webb Space Telescope is mapping its distribution through the phenomenon of gravitational lensing in galaxy clusters. When a massive galaxy cluster acts as a gravitational lens, the precise patterns of distortion, magnification, and multiple imaging that it creates in the light of background galaxies depend on the total mass distribution within the cluster, including the dark matter that dominates by mass over the visible galaxies and hot gas. By carefully modeling the lensing effects seen in JWST's deep images of galaxy clusters, astronomers can reconstruct detailed maps of the dark matter distribution within those clusters, probing the innermost regions and fine substructure of dark matter halos with unprecedented resolution. The detailed dark matter maps derived from JWST lensing studies are contributing to tests of dark matter models, including comparisons between the observed substructure of dark matter halos and the predictions of numerical simulations of structure formation in a universe dominated by cold dark matter. Type Ia supernovae, stellar explosions of approximately standardizable luminosity that can be used as cosmological distance indicators across billions of light-years, were the observational tools through which the accelerating expansion of the universe and the existence of dark energy were first established in 1998, and the James Webb Space Telescope is contributing to the continued study of these cosmic distance markers with infrared observations that reduce some of the systematic uncertainties that affect optical measurements. In the near-infrared, Type Ia supernovae show a narrower range of intrinsic luminosities than in the optical, making them potentially more reliable standard candles, and JWST's sensitivity allows high-quality near-infrared light curves to be obtained for supernovae at significantly greater distances than were accessible to previous space-based infrared observations. Beyond using Type Ia supernovae to measure the expansion history of the universe, JWST is also probing their progenitor systems, the binary star configurations that eventually trigger the thermonuclear explosion, by searching for infrared signatures in pre-explosion archival data and in the early-time emission of newly discovered events. Understanding what types of stellar systems produce Type Ia supernovae is important for assessing whether systematic differences in progenitor properties could introduce biases into cosmological measurements. Baryon acoustic oscillations, periodic variations in the density of visible matter imprinted by sound waves that propagated through the hot plasma of the early universe before the epoch of recombination, leave a characteristic scale in the statistical clustering of galaxies that serves as a cosmic standard ruler, providing a method for measuring the expansion history of the universe across billions of light-years. The characteristic scale of baryon acoustic oscillations corresponds to the distance that sound could travel through the early plasma before recombination froze the pattern into the distribution of matter, a distance of approximately 150 megaparsecs in comoving coordinates. The James Webb Space Telescope's spectroscopic capabilities are contributing to baryon acoustic oscillation surveys by measuring redshifts for large numbers of galaxies at a range of cosmic epochs, building three-dimensional maps of galaxy clustering from which the acoustic scale can be measured. By comparing the apparent size of the baryon acoustic oscillation feature at different redshifts with its intrinsic physical scale, astronomers can measure the expansion rate of the universe as a function of time, tracing the influence of dark energy on cosmic history. After the epoch of reionization concluded, the intergalactic medium settled into a state permeated by a diffuse ultraviolet background radiation field produced by the collective emission of distant quasars and galaxies, which maintained the intergalactic hydrogen in an ionized state and prevented it from recollecting into neutral clouds. The James Webb Space Telescope is studying the sources that contributed to this ionizing ultraviolet background by identifying and characterizing compact, intensely star-forming galaxies and luminous quasars at the tail end of reionization, the epoch between 1 and 2 billion years after the Big Bang, when the ultraviolet background was being steadily built up and maintained. Spectra of quasars at high redshifts observed by JWST show the Lyman alpha absorption forest, the series of absorption lines caused by patches of neutral hydrogen along the line of sight, whose statistical properties encode information about the density and ionization state of the intergalactic medium at different epochs. The evolution of the ultraviolet background over cosmic time, and its influence on the thermal and chemical state of the intergalactic medium, is a fundamental chapter in the history of the universe that JWST observations are illuminating with new precision. The way in which galaxies cluster together on large scales, the statistical patterns in their three-dimensional distribution across hundreds of millions of light-years, encodes a wealth of cosmological information about the density and nature of dark matter, the influence of dark energy, and the initial conditions of the universe as imprinted in the cosmic microwave background. The James Webb Space Telescope contributes to the study of large-scale structure by providing spectroscopic redshifts for large samples of galaxies in deep fields, building three-dimensional maps of the galaxy distribution that can be analyzed statistically to extract power spectra, correlation functions, and other clustering statistics. These measurements at high redshift, where the universe was substantially younger than it is today, provide a record of how the large-scale structure was assembled over cosmic time, allowing tests of theoretical predictions about the growth of structure under the influence of gravity, dark matter, and dark energy. The combination of JWST's deep spectroscopic surveys with complementary data from large area surveys being conducted by other facilities is building an increasingly precise and comprehensive observational foundation for cosmological parameter estimation. The age of the observable universe, approximately 13.8 billion years, as determined from the properties of the cosmic microwave background within the standard cosmological model, provides the temporal framework within which all of the James Webb Space Telescope's discoveries must be placed. Every distant galaxy that JWST observes is being seen as it appeared at some fraction of the universe's present age, from nearby galaxies just a few billion years old to the most ancient systems observed when the universe was only 2 or 3% of its current age. The flat geometry of the universe, established by measurements showing that the total energy density is equal to the critical density required for spatial flatness, means that light travels along straight paths through the cosmos, allowing the relationship between redshift and distance to be precisely calculated and JWST's observations to be precisely placed in the cosmological timeline. The convergence of measurements from the cosmic microwave background, galaxy surveys, and distance indicator observations toward a consistent picture of a spatially flat, approximately 13.8 billion-year-old universe is one of the great achievements of modern cosmology, and JWST's observations both depend on and contribute to the refinement of this picture. The abundances of the lightest elements, hydrogen, helium, and trace amounts of lithium, were established during the first few minutes after the Big Bang through a process called primordial nucleosynthesis, and the predicted ratios of these elements represent one of the most powerful tests of the standard cosmological model. The James Webb Space Telescope contributes to studies of primordial nucleosynthesis indirectly, by observing the most metal-poor galaxies and stellar populations that preserve the chemical composition closest to the primordial state, providing empirical constraints on the primordial helium abundance from the emission line ratios of ionized gas in these ancient systems. Measuring the primordial helium abundance is particularly important because it depends sensitively on the number of neutrino species and the expansion rate of the universe during the nucleosynthesis epoch, providing constraints on fundamental physics that cannot be accessed through any other means. The combination of primordial nucleosynthesis predictions with the baryon density measured from the cosmic microwave background and the elemental abundances observed in the oldest astrophysical systems provides a remarkably self-consistent test of the physics of the very early universe. The observable universe, the region from which light has had time to reach us since the Big Bang, extends approximately 46 billion light-years in every direction from our position, a sphere whose surface corresponds to the cosmic microwave background from which the earliest photons we can observe were released. The The James Webb Space Telescope can observe galaxies that emitted their light when the universe was less than 3% of its current age, probing the observable universe almost to its temporal limits, though the spatial limit of the observable universe extends far beyond even the most distant objects JWST can detect. Beyond the edge of the observable universe lies an unknown expanse of space that has existed since the Big Bang but from which no information has yet had time to reach us, a fundamental limit imposed by the finite speed of light and the finite age of the cosmos. The James Webb Space Telescope, by peering as close to this limit as current technology allows, is advancing humanity's exploration of the knowable cosmos toward its temporal boundary, illuminating the earliest chapter of the universe's story with unprecedented clarity and depth. The James Webb Space Telescope was designed with a minimum operational lifetime of 10 years, but the precision of its Ariane 5 launch and the efficiency with which it has consumed propellant during station-keeping maneuvers have led mission planners to estimate that JWST may continue operating for 20 years or more, well into the 2040s and potentially beyond. The propellant aboard the telescope, hydrazine and nitrogen tetroxide used for attitude control and orbit maintenance maneuvers around the L2 point, was the primary constraint on the mission's operational lifetime, as once it is exhausted the telescope will no longer be able to maintain its orientation and pointing. The launch accuracy achieved by the Ariane 5 rocket placed JWST on a trajectory so close to ideal that the propellant margins have been significantly larger than required for a 10-year mission, extending the estimated operational lifetime far beyond the original design goal. An extended operational lifetime means that the scientific community will have access to JWST's capabilities for a much longer period than was originally guaranteed, allowing more patient and comprehensive programs of observation to be pursued across all of its science themes. Every observation made by the James Webb Space Telescope, the raw data, the calibrated images, the extracted spectra, and the derived data products, is preserved in the Mikulski Archive for Space Telescopes at the Space Telescope Science Institute, where it is made freely and publicly available to researchers worldwide after a proprietary period of 12 months during which the original program's investigators have exclusive access. This vast and constantly growing archive represents a scientific legacy that will support research for decades beyond the telescope's operational lifetime, as new analysis techniques, improved calibration methods, and new scientific questions will find value in data that has already been collected and preserved. The JWST archive is carefully maintained with standardized data formats, well-documented calibration procedures, and tools for efficiently searching and retrieving data, making it accessible not only to professional astronomers but also to citizen scientists, educators, and students. The open-access nature of the JWST archive reflects a philosophy of scientific openness that maximizes the return on the collective investment in the mission by allowing the broadest possible community to draw scientific value from its observations. The James Webb Space Telescope does not operate in isolation but forms part of a rich ecosystem of space and ground-based observatories whose complementary capabilities collectively provide a more comprehensive view of the universe than any single facility could achieve. At shorter wavelengths, the Hubble Space Telescope continues to provide ultraviolet and optical observations that complement JWST's infrared perspective, and the two telescopes are frequently used in coordination to observe the same objects at different wavelengths simultaneously. At longer wavelengths, facilities like the Atacama Large Millimeter Array in Chile and the expanded Very Large Array in New Mexico probe the radio and millimeter wave emission from molecular gas, dust, and synchrotron radiation that JWST cannot observe, and planned coordination between JWST and these facilities is enabling multi-wavelength studies of unprecedented breadth. The complementarity of JWST with next-generation facilities currently in development or construction, including the extremely large telescope, the Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory, will further enhance the scientific productivity of each individual observatory by providing access to populations of objects and phenomena that each instrument alone cannot fully characterize. The Nancy Grace Roman Space Telescope, NASA's next flagship astrophysics mission, planned for launch in the mid-2020s and designed to complement the James Webb Space Telescope's deep but narrow field of view with a wide-field infrared survey capability, will open a new era of large-scale infrared astronomy by mapping large areas of the sky to depths comparable to Hubble's most intensive pointings. Where JWST observes with extraordinary depth over relatively small fields, Roman's 0.28 square degree field of view, more than 100 times larger than Hubble's Wide Field Camera 3, will enable statistical surveys of galaxies, exoplanets, and dark matter that require large sample sizes across wide areas of sky. The two telescopes are expected to work synergistically, with Roman's wide-field surveys identifying interesting targets for detailed follow-up with JWST's superior spectroscopic and imaging capabilities at longer infrared wavelengths. Together, JWST and Roman are expected to define the next several decades of infrared space astronomy, collectively addressing science questions that span from nearby solar system objects to the most distant galaxies at the edge of the observable universe. One of the most scientifically significant and carefully anticipated programs that the James Webb Space Telescope will pursue over its extended lifetime is the systematic search for potential biosignatures, chemical signatures in the atmospheres of rocky planets in the habitable zones of nearby stars that might indicate the presence of biological activity. The primary candidates for these biosignature searches are rocky planets orbiting nearby red dwarf stars, where the favorable geometry of transits and the proximity of the habitable zone to the small host star make atmospheric characterization most feasible with JWST's current capabilities. Key target molecules include ozone, which would indicate the presence of substantial oxygen, a gas that rapidly reacts with surface minerals and must be continuously replenished by a biological source to maintain atmospheric concentrations, as well as methane in the presence of carbon dioxide, a combination that would be chemically unstable without a continuous biological or geological source. JWST's biosignature searches will require many tens or hundreds of hours of observation per planet and will yield statistical detections rather than definitive identifications, but they represent the first systematic effort to search for evidence of life on planets outside our solar system using an orbiting infrared observatory. Despite the extraordinary discoveries already made in the first few years of James Webb Space Telescope science operations, many of the most fundamental questions about galaxy formation and evolution remain open, and the telescope's extended operational lifetime offers the opportunity to address these questions through larger statistical samples, deeper imaging, and more comprehensive spectroscopic surveys than have yet been conducted. The origin of the morphological diversity of galaxies, why some galaxies are spirals, some ellipticals, some lenticulous, and many are irregular, is intimately connected to the history of mergers, accretion, star formation, and feedback that each galaxy has experienced, and JWST observations across cosmic time are building the observational dataset needed to disentangle these contributions. The relationship between dark matter halo mass and galaxy stellar mass, and how this relationship evolved across cosmic time is a central test of galaxy formation models that JWST's deep spectroscopic surveys are beginning to constrain with new precision at high redshifts. The full picture of galaxy formation that will emerge from JWST's complete operational lifetime, combined with data from complementary facilities, promises to be substantially more complete and self-consistent than anything that has been possible before. Beyond its contributions to galaxy-scale and cosmological science, the James Webb Space Telescope is also making significant contributions to our understanding of individual stars and stellar physics, from the properties of the lowest mass brown dwarfs and M-dwarf stars through the evolution of massive stars toward their final explosive endpoints. JWST's infrared capabilities are particularly valuable for studying cool stars whose peak emission falls in the near-infrared, including the M-dwarf stars that are the most numerous type of star in the galaxy and the hosts of some of the most accessible, potentially habitable exoplanets. Observations of globular clusters, ancient, dense aggregations of hundreds of thousands of stars that represent some of the oldest stellar populations in the universe, are being used to refine models of stellar evolution at very low metallicities and to measure ages of these ancient systems with improved precision. The study of stellar physics with JWST ultimately connects directly to exoplanet science, because precise characterization of a planet's host star is essential for accurately interpreting the spectroscopic observations of the planet's atmosphere. The James Webb Space Telescope is also a powerful tool for studying transient astronomical phenomena, events that vary significantly in brightness or structure on timescales ranging from hours to years, including supernovae, tidal disruption events, gamma-ray burst afterglows, and the infrared counterparts of gravitational wave events. The telescope's infrared capabilities make it uniquely valuable for studying transients in dust-rich environments where shorter wavelength observations are obscured, and its combination of sensitivity and spectroscopic power allows detailed physical characterization of transient sources that shorter wavelength observatories cannot achieve. Coordination with gravitational wave detectors like LIGO and Virgo has enabled JWST to search for the infrared kilonova emission from binary neutron star mergers, events that are expected to be sites of heavy element production through the R process, the neutron capture nucleosynthesis pathway responsible for elements like gold, platinum, and uranium. The emerging field of multi-messenger astronomy, in which electromagnetic observations from facilities like JWST are combined with gravitational wave detections, represents one of the most exciting frontiers in astrophysics and one to which JWST is making growing contributions. The James Webb Space Telescope is the product of an international partnership among NASA, the European Space Agency, and the Canadian Space Agency, involving contributions from thousands of scientists, engineers, and technicians from institutions in more than a dozen countries over more than 2 decades. The scientific community using JWST's capabilities spans the globe, with principal investigators and team members from universities, research institutes, and space agencies in North America, Europe, Asia, Australia, and beyond, reflecting the fundamentally international character of modern astronomy. The telescope's science operations are managed by the Space Telescope Science Institute in Baltimore, Maryland, which coordinates the scheduling of observations, the processing of data, and the distribution of results to the worldwide scientific community. The spirit of international collaboration that characterized the construction and launch of JWST is carried forward in its science operations, where teams of astronomers from different countries work together on programs that address questions of universal significance, contributing to a body of knowledge that belongs to all of humanity. The James Webb Space Telescope represents one of humanity's most ambitious scientific endeavors, a 30-year journey from concept to launch, executed through the sustained efforts of thousands of dedicated individuals from around the world, that has placed in orbit an instrument of extraordinary power and sensitivity whose discoveries are only just beginning to unfold. The telescope's extended operational lifetime means that generations of astronomers who have not yet begun their careers will use JWST's capabilities to address questions that have not yet been formulated, employing analysis techniques that have not yet been invented to explore regions of parameter space that current observations are only beginning to define. The questions that JWST is currently addressing about the first galaxies, the nature of dark matter and dark energy, the compositions of exoplanet atmospheres, the chemistry of planet-forming disks, will evolve and deepen as the observational dataset accumulates, revealing new puzzles and unexpected connections that will guide the next generation of observatories and missions. The James Webb Space Telescope is, in the most profound sense, not just an instrument for the present generation of astronomers but a gift to all the generations that will follow, a quiet golden eye open upon the cosmos, patient and tireless, gathering light from the beginning of time. And so, dear listener, we come gently to the end of our journey through 110 quiet marvels gathered from the golden eye of the James Webb Space Telescope. A journey that has carried us from the delicate engineering of a mirror coated in gold, through the nurseries where stars are born, across the ancient light of the earliest galaxies, and to the very edge of what is knowable in the universe we inhabit. We hope that somewhere in the slow turning of these cosmic facts, in the patient distances and the soft glow of ancient light, you found a space wide enough to set down the weight of the day and rest. The universe is vast and unhurried. It has been quietly assembling itself for nearly 14 billion years and will continue long after all of us have rested. And in that immensity, there is a particular kind of peace. Sleep well, dream gently, and know that the telescope is still out there, gathering light in the silence between the stars.